Uncertainty in the behavior of humans on the road poses a major challenge to autonomous vehicles. To address this, many recent works learn models that generate distributions of agent future positions. There are many different representations used for predictions, with standardization nowhere on the horizon. This poses a challenge to planning algorithms, which currently are largely limited to Gaussian uncertainty. To address this challenge, this paper focuses on providing fast and general methods to assess the risk of a given trajectory. We are interested in risk assessment because it can be used as a subroutine to make search-based planners chance-constrained, and it can also be used to certify trajectories from deterministic planners. This problem is particularly challenging for autonomous driving because we need to certify events with very low probabilities, and also because autonomous driving has very stringent runtime constraints. We define risk at each time step as a probability of an agent entering an ellipsoidal set around the ego vehicle. We believe ellipsoids are useful because they can be fit fairly tightly to the profiles of vehicles. They can also be scaled to account for the sizes of the agent present. We transform predictions into the body frame of the ego vehicle, so the ellipsoid can be represented with a quadratic form parameterized by a constant matrix. We use this notation for quadratic forms and use x to denote the agent distribution. Now, this is the marginal risk at each time step associated with one agent. The paper discusses risk along the horizon, but we focus on these marginals in this video. For our experiments, we trained two deep nets on the Argoverse dataset and data collected from Carla. One predicts agent positions, the other predicts agent controls. Details and results are in the paper. We consider and provide solutions for three cases. We first consider the special case when Gaussian mixture models are used to represent future positions. The key takeaway is that this problem can be solved to arbitrary accuracy rapidly with numerical quadrature, but we omit it from this video for the sake of time. We then address the case when the mixture model components are not Gaussian but still have computable moments. And third, instead of position models, some works instead learn control models of agents. We address this case as well. And the general strategy is to propagate moments of the control distributions into position moments and then apply them other methods. In the case when the mixture model has non-Gaussian components but the moments of the components are still computable, we adopt two approaches. The first involves viewing the quadratic form as a random variable and applying the one-tailed Chebyshev inequality to it. This allows us to express a risk bound in terms of the first two moments of the quadratic form. Now, the key idea is that arbitrary moments of the quadratic form can be expressed in terms of moments of the agent position distribution. This allows us to express Chebyshev's inequality in terms of the first four moments of position distributions. Chebyshev's inequality can be conservative, but if we leverage higher moments, we can use them in a sums of squares program to solve for a tighter risk bound. Sums of squares programs can sometimes be conservative and scale poorly, but this particular one doesn't suffer from those issues as much, because it involves searching for a univariate as opposed to a multivariate polynomial. So it can explore the full space of non-negative polynomials, which multivariate SOS cannot, and the number of decision variables scales quadratically as opposed to combinatorially with respect to relaxation order. This program also becomes arbitrarily accurate as order goes to infinity. To give a rough sketch of the idea, we first note that the probability of violating any constraint on the agent prediction equals the expectation of an indicator function. Now, the key is to find coefficients such that the risk is upper bounded by a weighted sum of moments. And these coefficients are valid if and only if the polynomial defined by the coefficients upper bounds the indicator function. This condition can be enforced of SOS constraints, which are equivalent to convex semi-definite constraints. In practice, we found the optimizations to solve in 50 milliseconds or less. In the last case, we are given control instead of position distributions, so we need to compute the resulting position moments by propagating uncertainty through the nonlinear dynamics of the agent. Variants of the Kalman filter can be applied for this, but they are approximate. Instead, we develop an approach that is exact for systems that can be transformed into a polynomial system by developing an algorithm, tree-rain, that searches for a closed-form system of equations for the dynamics of the moments. For the problem of propagating agent controls, we are going to use the discrete time Dobbins car, with the time steps omitted for concision. This is our acceleration model, and this is our turning model for the agent. Now, this is not a polynomial system, but by making these substitutions, we can transform the Dobbins car into a polynomial system, so we can use it in tree-ring. And the general idea behind what tree-ring does is that for any moment we want to propagate, it first derives an update relation in terms of moments at the previous time step with the dynamics, and then factors terms in the update relation based off independence. And finally, it handles the unknown moments in the expression by deriving their dynamics as well, repeating this process recursively until it arrives at a closed-form system of equations.